In the heart of the unforgiving Taklamakan Desert, a place of nothing but sand, wind and scorching heat, China did something that caught the attention of engineers around the world. It built a railway network stretching more than 2,000 kilometers, slicing straight through billions of tons of shifting sand, to create one of the longest railways ever constructed in a desert environment. Building rail tracks in the middle of a desert is already an extreme challenge, costing over $3.5 billion, involving more than 12,000 workers over the course of an entire decade. The Taklamakan Railway today does more than connect remote oasis cities. It stands as a symbol of humanity's determination to push engineering to its limits. But how do you anchor steel rails onto a living sea of sand? Join Quantivox Tech as we uncover this massive project. For decades, China's northwestern frontier stretching across Xinjiang and the Darime Basin existed as a blank zone on the national map. It was an immense and isolated landscape divided by two towering mountain ranges and the vast Taklamakan Desert, which spans more than 127,000 square miles. In summer, ground temperatures here can soar above 160 degrees Fahrenheit, while in winter they plunge to -13 degrees. There is no water, no power infrastructure, and beneath every step lies only constantly shifting sand, offering no stable ground on which to build. Yet beneath this hostile ocean of dunes rest billions of tons of untapped resources: oil, coal, and most critically, rare earth elements. Materials widely regarded as essential to modern technological dominance. To access these reserves, China faced a stark reality, and there was no alternative but to attempt what was once considered an impossible undertaking: constructing a railway across the desert. This led to the creation of the Hotan-Rukiang Railway, an 890-kilometer line forming part of the Taklamakan Desert Loop, a 2,685-kilometer circular railway system running along the desert's southern edge. Completed in June 2022, it now stands as the longest railway ever built through a desert. As a first step, hundreds of bulldozers were deployed to level the sandy surface to create a construction site in the middle of the desert, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems push the excess sand away from the work zone, while compactors gently press the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. After the surface had been compacted, workers began spreading a base layer of soil over the stabilized sand. Dump trucks poured out loads of reddish earth, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted, forming a dense, stable base strong enough to support the first stages of construction in the desert. Once the ground base was fully stabilized, workers began erecting the bridge pillars. To build them, they had to drill through dozens of feet of loose sand until reaching the solid gravel or compact soil beneath reinforced concrete. Pile drivers operated day and night, using steel casing pipes and bentonite slurry to keep the boreholes from collapsing. Concrete was poured from the bottom up through TREME pipes to prevent air pockets, while the steel cages were positioned with millimeter precision. Even the slightest misalignment could cause the pile to tilt or lose stability, because daytime and nighttime temperatures differed by more than 130 degrees Fahrenheit. Construction crews worked mostly at night when the wind was calm and the sandstorms eased. Thanks to these steel and concrete piles, the railway's foundation seemed to grow roots deep into the desert. On top of those foundations, 11,000 bridge piers began to rise row after row, forming a vast concrete forest stretching across the desert. Each pier stood between 16 and 50 feet tall. The shafts were cast using slip-form molds reinforced with galvanized steel and salt-resistant additives to withstand the desert's corrosive climate. The short, uniform spans between piers were designed to minimize the effects of wind and extreme temperature changes. As the sun set behind the Conlan Mountains, the endless lines of pillars stretched toward the horizon, a skeleton of steel and concrete unshaken by the desert winds. On top of those pier caps, thousands of pre-stressed concrete box girders were lifted into place using heavy crawler cranes or self-launching gantries. Each girder was over 100 feet long and weighed several hundred tons. They were transported on specialized flatbed rail cars and hoisted one by one onto the piers. Engineers then aligned the girders with laser precision, keeping tolerances within just a few millimeters. Once the spans were secured, crews poured the bridge deck slabs or installed precast concrete panels, forming a smooth surface for the tracks. Every span was spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. More than 65% of the Hote-Rokian Railway, about 310 miles, runs on these elevated viaducts. From above, the railway appears like a silver ribbon cutting across an ocean of gold. A living monument to human ingenuity against one of Earth's harshest landscapes. Next, these concrete blocks being installed are called sleepers or railroad ties. They're placed evenly along the track bed to hold the steel rails in position and distribute the weight of passing trains. Workers align each sleeper precisely, then use a lifting frame to lower the rails onto them. Once fixed and fastened, they keep the track straight and stable, preventing it from bending or shifting under heavy loads. A crucial step before the trains can safely run through the desert. After the sleepers were secured, crews began laying the steel rails on top. Each rail, stretching more than 260 feet long, was lifted into place by specialized cranes and carefully aligned along the center line. Workers adjusted every joint and gap to allow smooth expansion under heat, then tightened the fastening clips that locked the rails onto the concrete base. It took 11 months of continuous work to complete the hundreds of miles of track stretching across the desert. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement vibration, rail temperature, and wind-induced sway. The bridges were load tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters even after hundreds of test runs. Thanks to the elevated design and natural airflow beneath the viaducts, no sand accumulated on the tracks. All operational data flowed to the control center through IoT sensors and solar-powered cameras that monitored every section in real time. After 6 months of rigorous testing, the Hotan-Rokiang Railway officially opened in June 2022, completing the 1,685-mile loop that circles the Taklamakan Desert. In the United States, most railway lines are still built using the traditional method, with thick layers of crushed stone known as ballast laid beneath each rail. This seemingly simple material plays a crucial role. It distributes the train's weight, keeps the track structure stable, and allows rainwater to drain away from the track bed. China, on the other hand, has taken a completely different path. On its next-generation high-speed railways, the traditional layer of stone has been replaced by a continuous concrete foundation known as slab track. Here the rails are fixed directly onto the concrete surface, aligned with laser systems, and installed by fully automated machinery. Instead of loose stones, the entire structure becomes one unified body, stronger, more durable, and incredibly precise as a result. Chinese trains can travel smoothly at speeds exceeding 350 kilometers per hour. And now we're going to the construction site to see how they complete thousands of miles of railway. The subgrade is prepared by grading and compacting multiple layers of soil and gravel until a firm foundation is achieved. Typically about 2 to 4 feet deep, depending on terrain and expected train loads. Once the base is stable, engineers begin spreading the ballast. Unlike concrete, this layer isn't bonded together. It remains loose to absorb vibration and allow rainwater to drain freely through the track bed. 1 mile of track requires nearly 3,500 tons of ballast, around 7 million pounds of stone. The ballast is released from specialized hopper cars and then leveled evenly by a ballast regulator. A machine fitted with plow blades, rotating brushes, and laser-guided leveling boxes. Modern versions produced by manufacturers such as Placer and Thor can operate with minimal human input, automatically adjusting height and slope within minutes. After distribution, powerful vibratory compactors press the ballast into place, creating a dense and perfectly stable foundation. Completing just 0.6 miles of track can take anywhere from several hours to a few days, depending on soil conditions and site terrain. After the ballast layer has been evenly distributed and roughly leveled, construction crews move on to positioning the sleepers, the foundation pieces that define and lock in the exact alignment of the entire railway track. In most modern railway projects, this process is performed by an automatic sleeper laying machine. Using powerful hydraulic clamps, the machine lifts each sleeper weighing between 600 and 700 pounds and places it precisely according to its marked position. Each sleeper is spaced about 2 feet apart, and during a single shift the machine can install more than 2,000 sleepers with remarkable accuracy. Sleepers can be manufactured from several materials. Traditional ones are made of wood, pressure treated with creosote oil to prevent rot and reduce vibration. However, their lifespan is limited to around 20 to 30 years. Today, reinforced concrete sleepers have become the industry standard, heavier, stronger, and capable of lasting over 50 years while supporting much greater loads. For maintenance or track renewal projects, engineers often use panel track systems, pre-assembled rail and sleeper sections built in factories. Once thousands of sleepers have been positioned with precision along the prepared route, the next stage begins. Rail laying. Each steel rail, typically 78 to 80 feet long and weighing around 1,300 pounds, is delivered to the site on specialized transport vehicles known as rail trains. In modern railway construction, engineers often rely on continuous welded rails, CWR, long steel segments pre-welded at the factory, each stretching up to 1/4 mile in length. At the work site, the rail train gradually feeds these immense steel ribbons from the rear while hydraulic winches pull them forward and align them along the track bed. Workers guide the rails to glide smoothly over the ballast, positioning them perfectly atop each sleeper and holding them in place with temporary steel clips or pins. Once alignment is confirmed, the rail tensioning phase begins. Each rail is stretched or anchored using hydraulic tensioning machines to account for thermal expansion and contraction, a vital step that prevents future warping or buckling. After the rails have been perfectly aligned in place, the next step is to install the rail fastening system, a network of smaller components that keeps the entire track secure and stable. Each fastening assembly is made up of a steel base plate, rubber pad, spring clips, and anchor bolts. The base plate evenly distributes the wheel load from passing trains across the sleeper, while the rubber pad beneath it cushions vibration and helps reduce noise. Workers move steadily along the track, fitting each set of fasteners into position and tightening the bolts with torque wrenches to the precise specification, ensuring every joint applies the same uniform pressure. Once the bolts are secure, the clips are locked into place, holding the rail firmly against the base plate while still allowing slight flexibility for thermal expansion and contraction as the steel responds to temperature changes. Once the entire fastening system has been installed, engineers move on to the stage of track alignment and ballast tamping, a precision process that determines how smoothly a train will glide over the rails. A specialized tamping machine travels slowly along the track at an average speed of 0.3 to 0.5 miles per hour, equipped with dozens of hydraulic vibrating tines. During operation, the machine lifts the entire rail and sleeper assembly by about 1 to 2 inches, while the vibrating tines compact the ballast beneath at a rate of roughly 35 to 40 vibrations per second. This synchronized motion locks the crushed stones tightly together, creating a dense yet flexible foundation capable of absorbing impact and maintaining long-term track stability. Meanwhile, laser sensors and gyroscopes continuously measure elevation, tilt, turn, and alignment. Any deviation, even as small as 1/10 of an inch, is instantly detected, and the system automatically corrects it to match design standards. With this level of automation, a 1-mile section of track can be fully aligned and tamped in just 2 to 3 hours, making the process more than 10 times faster than traditional manual methods. Once the entire track has been precisely aligned, engineers proceed to the rail welding phase. Two main techniques are typically employed: flash butt welding and aluminothermic welding. In flash butt welding, the two rail ends are clamped tightly together by an electric welding machine. A powerful current passes through the joint, heating the steel to nearly 2,700 degrees Fahrenheit until it softens, melts, and fuses into a single continuous rail. In more confined or remote areas where access is limited, engineers rely on aluminothermic welding instead. In this process, a mixture of aluminum powder and iron oxide is ignited inside a cast iron mold, triggering an exothermic reaction that can reach temperatures of up to 4,500 degrees Fahrenheit, hot enough to liquefy steel and fill the gap between the rail ends. Once the molten metal cools and solidifies, the excess material is trimmed. Often the joint is polished using a rail grinder, removing any ridges or surface irregularities to ensure a perfectly smooth and seamless running surface. So you've now explored the entire rail installation process used by both the Americans and the Chinese. Which approach do you think is smarter and more practical? Let me know your thoughts.